Welcome to lecture 3. So let's start lecture 3 with concentration cells. So what is a concentration cell? So a concentration cell basically exploits the effect of concentration changes on a cell potential. So what we are doing here is that both the anode and cathode are of the same material but of different concentrations. So we are basically changing the concentrations in a way to make one of them the anode, the other the cathode, and drive the reaction. So the cell will have the same half reaction in both cell compartments but with a different concentration of electrolyte. So on one case you have the anode, which is the lesser concentration one, which results in oxidation, and you have a cathode that has a higher concentration, which it becomes the anode. So remember that here we're trying to drive the molecules from the anode towards the cathode. So from lower concentration to the higher concentration. So as long as the concentration of the solutions are different and the cell potential is greater than 0, the cell can do work. So this is the same exact principle that human cell uses to communicate as well. So the sodium potassium pump between the intracellular fluid and the extracellular fluid use the exploitation of the concentration difference between these two molecules to drive the potential to drive the electrical impulses to travel through the nerves. So this is one of the main ways for concentrations to work. So a concentration cell, generally based on copper half reaction, looks somewhat like this. So you have the 0.10 m copper on one side and 1 m copper on the other side. Here we are using the same solid material, but we are changing the concentration of the ionic solution that is present in the electrolyte. So the concentration will drive in such a way that the copper will try to accumulate on one side, resulting in an equality of concentration. So when both jars reach equal concentration, the amount of the voltage will become nearly 0. So the cell here will no longer be able to do work once the concentrations become equal. So let's take a problem. So a concentration cell consists of two silver half cells, and in half cell A the electrolyte is 0.010 m AgNO3, and in half cell B it's 4 times 10 to the power negative 4 m AgNO3. So what is the cell potential at 298.15 Kelvin? So let's take the value right here. So we know that the cell potential is given as the standard cell potential minus 0.0592 over n log Q. So we know that because it's the same reaction, so the standard cell potential becomes 0 because both of them have the same both of them will have the same half cell potential. So therefore the cell potential is 0. So the actual cell potential becomes negative 0.0592 by n log Q. So let's take the reaction right here. So on one side you have Ag that results in Ag plus an electron. So here, which is the anode, and this undergoes the oxidation reaction. And the other side you have Ag plus 1 electron, resulting in the formation of Ag, so which is the cathode, and reduction. So this here has a concentration of 0.010 m on one side. You have on the other side you have 4 times, lower concentration one is the one that undergoes oxidation. So 4.0 times 10 to the power negative 4 m, and this has a concentration of 0.010 m. So now we have to calculate the total reaction. So the full reaction becomes, so the electron get cancelled. So Ag plus gives Ag plus Ag. So now how would you calculate the difference here? Notice here that you have two different Ags. So on one side you have the high concentration Ag plus, on the other side you have the low concentration Ag plus. So let's consider this the concentrated one and this is the dilute one. So we know the formula for Q. So the Q here is, this is Ag concentrated and this is Ag dilute. So this is going to be Ag plus dilute times Ag over Ag plus concentrated by times Ag. So the Ag concentration will not match. So we have to calculate Ag dilute by Ag concentrated. So Ag dilute is this value and Ag concentrated is this value. So you have 4 times 10 to the power negative 4 divided by 0.010 m. So let's try to calculate that value. So 4 times 10 to the power negative 4 divided by 0.010. So that gives you a value of 0.04. So that's the Q value. Now substitute that value into the cell potential. Notice that here there's just one electron transfer. So the N value becomes 1. So we have N equals 1 and Q equals 0.04. So now the cell potential is negative 0.0592 by N log Q. So that becomes negative 0.0592 by N is 1 times log of Q is 0.04. So now 0.04, sorry. So negative 0.0592 times log 0.04. So that gives you a value of 0.0827. So which when rounded off will give you a value of 0.083 volt. So the cell potential is 0.083 volt or 83 millivolt. So 83 millivolt. So this is the cell potential value, and this is how you can calculate the cell potential. So one of the best understanding of uses of this is the use for calculating the pH. So we can use the cell potential value and calibrate that value to give you the pH value. So the same principle applies here. So the operation of a pH meter illustrates an important application of the concentration cells. So the glass electrode here monitors the H plus solution relative to its own fixed internal H plus. Now when it changes, what happens now here is that there is a change in the potential, there is change in the concentration. Therefore there is going to be a production of potential. So that potential can be calibrated to create the value of the pH. So some ions that are generally used measured with ion specific electrodes, for example industrial water, wastewater and seawater can be used by using ammonia. Blood and groundwater can be done by using bicarbonate ion, and drinking water, urine, soil, industrial stack gases can be used by using fluorine. Grain and plant tissue by bromine, milk and pharmaceuticals by iodine, soil, fertilizer and drinking water by nitrates, blood serum, soil and wine by potassium, laboratory solutions, soil, natural waters by hydrogen. So a mini microelectrode is generally a common way to record the electrical impulses of a single neuron in the monkey's visual cortex. So the electrical potential of a nerve cell is due to the difference in the concentration of potassium and sodium ions inside and outside the cell. This is how electrical impulses create the action potential. The action potential therefore conducts the nerve impulses from one position to the other position. Next, let's talk about electrochemical processes in batteries. So a battery generally consists of a self-contained voltaic cells arranged in a series, so their individual voltages are added. So when you have a primary battery is something that cannot be recharged. So once it reaches equilibrium, it's a dead battery. So whenever you see the term dead battery, it basically means that it's a primary battery, and therefore the cell reaction has reached equilibrium, thereby it does not undergo any further use. A secondary battery is a rechargeable battery. So once it has run down, the electrical energy is supplied to reverse the cell reaction and form more reactant. So this is an example of an alkaline battery. An alkaline battery generally consists of a graphite rod acting as the cathode, and you have manganese oxide in a potassium hydroxide paste inside the material, and you have a zinc anode on the outer shell. and you have the negative end of the cap and the positive end of the cap. The positive end of the cap generally connects to the graphite rod, and the negative end of the cap is generally connected to the zinc. So causing this reaction where the manganese oxide and zinc exchange the electrons, resulting in a cell potential of around 1.5 volts. Next, let's talk about a silver button battery, most commonly used in watches and really small equipment. So this also uses the same principle, but rather than having manganese oxide, you have silver oxide, which results in the overall potential of around 1.3 volts. Next, you have a lithium battery. A lithium battery most commonly used in watches, implanted medical devices, and remote control devices, uses lithium and silver vanadium oxide to create the overall cell reaction, which gives you around depending on the type of device that you use, you have different levels of energy that is being produced. And you have a lead acid battery, most commonly used in automobiles. So it's a secondary battery, which means it's a rechargeable battery. So you have anode generally filled with spongy lead, and cathode generally filled with lead oxide. So the spongy lead undergoes the reaction, thereby resulting in the reverses the reaction. The electrolyte here acts as the sulfuric acid acts as the electrode. Now the positive end and the negative end are on the top of the battery, thereby resulting in the production of the potential. So in the lead acid battery, you use concentration cell reactions to produce an overall cell potential of around 2.1 volts. Next, you have a nickel metal hydride battery, most commonly used in high energy uses, most commonly in a drill bit batteries. So these contain nickel oxide as the anode and any metal hydroxide as the cathode. Next, you have a lithium ion battery. Lithium ion battery uses the same principle of a concentration cell, resulting in one side you have the lithium in graphite acting as the anode, and lithium manganese oxide acting as the cathode, with an electrolyte of lithium phosphorus fluoride in dimethyl carbonate solution. So this is generally used to power laptops, cell phones, and camcorders. So with a cell potential of around 3.7 volts. So this is the common cell potential that you see in lithium ion batteries. Next, let's talk about fuel cells. So in a fuel cell, most commonly also called as a flow cell, so reactants enter the cell and the products leave, generating electricity through controlled combustion. So the reaction rates are lower in fuel cells than in other batteries, so that an electrocatalyst is used to decrease the activation energy. So in a hydrogen fuel cell, you have hydrogen on one side entering and oxygen on the other side entering. Now both of them will undergo a reaction producing water vapor. The water vapor passes through the electrolyte, which is the polymer membrane sulfonated perfluoroethylene, so which uses that water vapor to produce the overall reaction of creating water, resulting in the cell potential of around 1.2 volts. Most commonly these days, these are being tried on automobiles to make sure that we can produce energy by using hydrogen and oxygen, where the byproduct is relatively harmless water. Let's talk about the final topic, corrosion. So corrosion, basically an environmental voltaic cell. So corrosion is the process whereby the metals are oxidized to their oxides and sulfides. So most common example of this is rusting of iron. So is a common form of corrosion. So rust is not a direct product of the reaction between iron and oxygen, but arises through a complex electrochemical process. So rusting generally requires moisture and occurs more quickly at low pH in ionic solutions and when the iron is in contact with a less active metal. So the loss of iron is the main principle of rusting of iron. So iron undergoes oxidation and the oxygen takes the electrons to form water. So this thereby creating more and more rusting process where you create a ferric oxide, ferric hydride. So the very ferric oxide hydrate, which results in the rusting of iron. So the hydrogen ions here are consumed in the first step. So lowering the pH increases the overall rate of the process. So the H plus ions here act as the catalyst. So main thing to remember, since these are the ones that are regenerated in the second part of the process. So this is a simple example of the process where you have iron that is combining with the water vapor, resulting in a pit, and on one side you have the water vapor again reacting to form the rust oxide, so thereby creating this continuous cycle of erosion of ions. So one of the ways we can reduce this is by use of sacrificial rods to prevent iron corrosion. So for example, if you use a more active metal, so rather than rusting the iron here, the magnesium rod generally undergoes a much more corrosion, so resulting in what we call as a sacrificial anode. So here we use an active metal such as zinc, magnesium or aluminum acts as the anode and is sacrificial instead of iron. So let's come to the final part, electrolytic cell. So what is an electrolytic cell? So in simple sense, electrolytic cell uses an electrical energy from an external source to drive a non-spontaneous redox reaction. So the reaction that it tries to run here, for example, copper undergoes oxidation and tin undergoes reduction, resulting in a negative cell potential where the free energy is greater than usual. So as with voltaic cell, oxidation occurs at the anode and reduction takes place at the cathode. An external source supplies the cathode with electrons, which is negative, and removes the anode, which is positive. So remember this concept, it's the opposite in an electrolytic cell. So in a voltaic cell, you have lead and copper. So the lead, which is negatively charged, which becomes the anode, and the cathode is positively charged. In an electrolytic cell, cathode is negatively charged and anode is positively charged. So that's the main difference here. So what in terms of the differences here, the electrolytic cell generally has a free energy greater than 0 and a cell potential less than 0. So therefore the anode becomes positive and the cathode becomes negative, and the anode is where the oxidation takes place, but the oxidation is generally given a positive sign and a reduction is given a negative sign in the electrolytic cells. So next, let's talk about products of electrolysis. So electrolysis is the process of splitting of a substance by the input of electrical energy. So during electrolysis of pure molten salt, the cation will be reduced and the anion will be oxidized. Remember this principle, that cation is the one that undergoes reduction and the anion is the one that undergoes oxidation. So during electrolysis of a mixture of molten salts, the more easily oxidized species reacts at the anode and the more easily reduced species reacts at the cathode. So let's take a simple example. A chemical engineer melts a naturally occurring mixture of sodium bromide and magnesium chloride and decomposes it at an electrolytic cell, predicts the substance that forms at each electrode, and write the balanced half reactions of overall reactions. Now, what is generally a good oxidizing agent? So an oxidizing agent is the one that tries to gain more electrons faster. So if a material tries to gain electrons faster, it must have a higher ionization energy. So a metal that can hold its electrons more tightly than ever generally has a higher ionization energy. So its cation will generally gain electrons more easily, thereby it will become a strong oxidizing agent. If a non-metal holds its electrons less lightly than another, it will generally have a lower electronegativity, so its anion will lose electrons more easily and then it will become a reducing agent. Let's take sodium and magnesium and bromine and calcium. So the positive oxidizing species are sodium and magnesium, which is positively charged ones, which are generally the ones that have high ionization energy. And possible reducing species are bromine and calcium because they already have full octet orbitals. Now let's take the difference between here. Let's talk about magnesium first. So magnesium requires 2 electrons for it to undergo reduction, while sodium requires only 1 electron to undergo oxidation. Now bromine here requires 2 electrons to undergo. So 2 bromine molecules are required for the overall cell reaction of magnesium and bromine. The reason why magnesium and bromine are the ones that undergo the reaction is mainly because chlorine is relatively smaller in comparison to bromine. Thereby, it's not that easy to remove electrons from chlorine, but rather it's easy to remove electrons from bromine. The main reason is because it's large. The same thing happens here with magnesium. Magnesium, because it has a larger effective charge, which results in an easier reduction process rather than comparison to sodium, which only has one single effective charge, only one charge on top of it. So therefore, magnesium and bromide are the ones that accumulate on the cathode and anode respectively. So electrolysis of water results in the formation of hydrogen and oxygen. So this is a simple description here. So you have the oxidation half reaction where water splits into oxygen, resulting in the release of 4 electrons. In the reduction half reaction, the water takes the electrons and forms hydrogen and OH minus ions. So the resultant product will try to balance itself to create the same amount, thereby releasing. So the water is utilized to create H2 and O2. So let's next electrolysis of aqueous salt solutions. So when an aqueous salt solution is electrolyzed, so the strong oxidizing agent is reduced and the strong reducing agent is the oxidized one. So the strong oxidizing agent is the one that has the most positive electrode potential, and the strong reducing agent is the one that has the most negative electrode potential. So over voltage is the additional voltage needed above the cell potential values to produce gases at the metal electrodes. So over voltage needs to be taken into effect whenever you're trying to predict the products. So this is around 0.4 to 0.6 volts for hydrogen and oxygen. So this is the summary of aqueous salt solution. So what products are formed at which electrode during the electrolysis of aqueous solution of the following salts? So first we are using KBr. So KBr contains potassium. So potassium has a cell potential value of negative 2.93, while water has a cell potential value of negative 0.42. Now one that is more negative, so the one that is most positive will be the oxidizing agent, will become reduced. So which means the one that is going to get reduced is water, the one that gets oxidized is potassium. So when you calculate the cell potential, so you have negative 0.42 minus of minus 2.93. So you will need about minus 0.8 to 0.1.0. So next let's talk about the stoichiometry of electrolysis. So we use the Faraday's laws of electrolysis. So it basically states that the amount of substance produced at each electrode is directly proportional to the quantity of charge flowing through the cell. So we know that the current flowing through the cell is generally amounts of charge per unit time. So current is measured in amperes. So we can write that current times time equals charge. So first we take the mass of the substance that is oxidized reduced and multiply it, so divide it with the molar mass, resulting in the amount, the number of moles. And using the balanced half reaction, we calculate the amount of number of moles transferred. And finally, we multiply with the Faraday's constant to calculate the charge, and finally gives you the current. So let's take an example right here. So a technician plates a faucet with 0.86 grams of chromium metal at by electrolysis of aqueous chromium sulfate. If 12.5 minutes is allowed for the plating, what current is needed? So let's first take into process the amount that is given. So you have 0.86 grams. So the mass here is 0.86 grams. And the amount of time taken is 12.5 minutes. And we are using chromium sulfate. So for this to split, the reaction gives you 2 Cr3 plus 3 SO3 2 minus. So this is how chromium will generally split. Now let's take into account the reaction right here. So you have Cr3 plus, so which undergoes to become chromium. So for this reaction on this side, we'll have to add 3 electrons to this to create chromium. So the total number of electrons is 3 electrons. Now for it creates 0.86 grams of it, so we need to calculate the number of moles of chromium. So to calculate the number of moles of chromium, so we just have to divide it by the mass by molar mass. So what is the mass here? Is 0.86 grams, and the molar mass of chromium is 52. So which gives you a value of 0.050 moles of chromium. So this is the number of moles of chromium. Now we need to calculate the moles of electrons being transferred. So for 1 mole of chromium, there's about 3 moles of electrons. So because there is per mole of chromium, there's 3 electrons being transferred. So the number of moles of electrons becomes 3 times the amount of chromium. So the number of moles of chromium. So 3 times the number of moles of chromium is 0.050. So which gives you a value of 0.15 mole. So this is the number of moles of chromium that's being transferred. Now let's try and calculate the charge. So the charge can be calculated. So it's the number of moles of electrons being transferred times the Faraday's constant. So the number of moles of electrons that being transferred is 0.15 times the Faraday constant. I am sorry. .86 divided by 52. So this value is 0.01653 mole. So this value now becomes 0.01653 times 3. So now this gives you a value of 0.05 mole. So the total number of moles of electrons that's being transferred is 0.05. Now multiply it with the Faraday constant, so which is 9.65 times 10 to the power of 4 coulomb per moles of electrons. So this is the moles of electrons. So moles of electrons cancel. Now you'll end up with the charge, so which is going to be 0.05 times 9.65 times 10 to the power of 4. So that gives you 4825 coulomb. So that's the amount of charge that's being transferred is 4825 coulomb. So we know that current is charge over time. So the time here is given as 12.5 minutes. So we can combine that. So we have 12.5 times 60 seconds per minute. So that gives you a total of 750 seconds. So you have charge which is 4825 coulomb over 750 seconds. So 4825 divided by 750. So that gives you 6.43 amps. So the current here required for that much amount of electroplating is 6.43 amperes. So remember that charge is number of moles times the Faraday's constant. So with that, we end the topic on electrochemistry. I will see you all again in the next.